All right, so I said in an earlier video that the wave function psi contains all the information you need to know about a particle. Usually an electron, could be another subatomic particle. One of the things you can do with psi to extract some information is you can calculate the average you would expect to get from a measurement. Let's suppose, for example, you're trying to measure the position of an electron. Average could mean one of two things there. Either you prepare separate trials with an electron and you measure the position with those separate trials, or maybe you have an ensemble of electrons and you're getting the average of that ensemble. This averaging process works the same way. The point of calculating this average is, what do you expect to get for the value for the measurement of the position? And that's why we call this thing an expectation value. The recipe is this: if you're trying to measure a thing, call it M, right? M for measurement. The way we denote an expectation value is with these little wedges here. So this is like saying, here's the average that you expect to get. Everything should be within some range of this value. The way you do this is you take an integral. You take psi star, the complex conjugate of your wave function. You take a psi, and then you place this measurement in the middle, and you integrate over all the space that you're interested in. And inside this M, you need to make a couple of replacements. Anytime you have the position, you're just going to multiply by x, right? We saw that earlier. X gets to be an easy operator in quantum mechanics. Momentum, on the other hand, turns into h bar over I, first derivative with respect to x. And that's why this order actually matters. You don't get to just flip these things around, because this thing is now an operator acting on this psi. So you're taking this operator acting on psi, then you're multiplying by psi star, then you're doing the integral. So you're kind of taking it in this sort of layered approach. Here you got this piece, then you have this piece, and then you have this piece. All right, so that order is very important. Let me show you an example. Let's suppose you were trying to do the expectation value of the momentum. You're trying to get an idea of how fast the electron is going. So you'd have to take integral psi star, momentum operator gets replaced by h bar over I, d by dx of the psi over here. Now here's where things get interesting, right? This is an average value for a measurement. You have never seen a measurement of momentum that was imaginary or complex. There shouldn't be any eyes on your momentum meter or your position meter or your energy meter, whatever it is you're using to measure something in this problem. There should not be any eyes left over. So this thing needs to end up being real. And on the surface here, it kind of looks like this is going to have an eye in it. And so by the end of our derivation here, we need to check to make sure this expectation value is always real. So whenever you're calculating an expectation value, make sure there are no eyes left over. If you have an eye left over, you did something wrong. There's no nice way to say it. You have a mistake somewhere. It's okay. You go back to fix it. But if you have an eye left over, that is a thing you need to check for and that you need to go back and address. Okay, let's take a look at how this thing works out. So remember that your wave function you can always write as real plus I times the imaginary part. Well, same thing over here. So we'll have our complex conjugate. So real minus root negative 1 times I, h bar over I, d by dx, real plus I times imaginary part, dx. And so basically, whatever happens with this derivative, right, I can distribute this derivative to get dr dx plus I di dx, right? Whatever happens with that derivative, all of those i's need to end up going away by the end. Now, of course, this is also an integral. Let's put that part on hold for just a second, because I've also got to do this integral, right? And integrals I can't always do by hand. So let's transform this integral into something that we can feed into the computer. All right, so here's the integral we're trying to take. Now, the way you do an integral on a computer is, instead of thinking of it as a nice smooth function, you have to think of it as small pieces, right? You're adding up small little strips of area in a Riemann sum. So we need to replace this with a sum over our grid spacing, right? Because the beautiful thing is, in our code, we already have this grid spacing, right? For x, we already have this labeled j to be 0, then 1, then 2, then 3, etc. We've already got those strips set up, so let's just use that same set of strips spaced out by dx for our integral that we're already using for our difference equation. So we need to sum this over j. And let's see, let's get a big bracket. So here I've got my real part of the wave function. So that's going to be r jk minus imaginary value I, imaginary part, times jk. Let's see here. I have an h bar over I on everybody, so let's just factor that out. So we're going to hope that everything inside the square brackets ends up having an I, so I can just cancel with this I over here. And then I've got my derivatives here. And you remember our recipe for calculating a derivative, right? I just take the point to the left, my point to the right. So let's take rj plus 1 comma k. And then I need a point to the left. Now for the time derivative, we were taking this as the next value minus the current value. Here I'm going to do it a little bit different. I'm going to make this rj minus 1 comma k. The reason I want to do that is because it's a little bit more accurate and it's a little bit better in terms of the spatial symmetry. Right, with time, I can only move forward, but with space, I can move left and right, so I might as well use that information. The difference here is I'm moving 2 units, right? So if I'm interested in the derivative at this point, I'm going to the left one and I'm going to the right one. That total distance here is 2 times dx. So I need a 2 dx down on the bottom here. If you want to, you can go in and change the code to be j plus 1 and j. You'll have a lot to change in the code, so you could just stick with this if you'd rather not have to do that. So we'll say plus I times this thing. So I need to apply the same thing to the imaginary part. So I, j plus 1, comma k, minus I, j minus 1, comma k, divide by, again, 2 dx. And then I have everybody being integrated over x, so everybody needs to get multiplied by dx. So this dx is just the discretized version of this dx over here. I probably should have called this a delta x or an h, but I chose that in the first video, so that's what I'm stuck with. Okay, so this is the expectation value for p. So we need to factor this part out and see what happens with these i's. Okay. So let's see here. So I've got my dx h bar over I out front. Let's see here. Everybody inside here is being divided by a 2 dx. So I can put a 2 dx out here, right? Because this term is being multiplied by this term, so I can factor out a 2 dx from the entire summation. That means this dx's actually cancel, which is kind of nice because it means I can just use my function values. I don't have to actually worry about how spread apart they were. So I have an h bar over 2I, I'll clean that up on the next line. We've got a summation over j, right? We're not summing over k, because this is actually the expectation value at time k. Because your expectation value, it doesn't have to be constant. It can be changing with time. In fact, you would expect it to be changing with time, wouldn't you? Like you wouldn't expect the mass of particles just stay put. You would expect that average to move around with time. So I've got sum on j here. And now I basically just need to do a little bit of foiling here. So let's see. So I'm going to have an rjk times this piece. So I'll have an rj plus 1k. All right, and then I'll have a minus rjk times rj minus 1k. So I've taken this piece right here, this rjk, and distribute it to these two. Now I need to take this rjk, distribute it to these two. So I'll have a plus I, square root of negative 1, rjk times ij plus 1k. And so at this point, I'm going to dispense with the commas. I assume you know how to read these by now. Let's see, then we'll have a minus I. Same thing over here, rjk ij minus 1k. All right, let's just do a quick little sign check here. I got rjk. These two should give me a positive. That's a positive. These two should give me a negative. That's a negative. These two should give me an I. That's an I. These two should give me a negative I. That's a negative I. Now do the same thing with this guy. All right, so I will have a minus imaginary number, imaginary part, ijk, multiplied by this thing, rj plus 1k. Now I have a negative times a negative. They give me a positive. I still have an I, ijk, rj minus 1k. Cool. Now we'll move on to this part. All right, I have a negative. This is where we have to, really, the i's and the r's, the capital I's and the capital R's are easy to keep track of. It's the i's, the lowercase i's, you have to watch out for now. So I have negative I times a positive I, right? I squared gives you negative 1, right? That's something you should be doing automatically by now. If I make it a negative I squared, though, then it's a positive 1. So I just have a plus ijk, ij plus 1k, right? And then I come at last to this part. I have a negative times a negative gives me a positive, and I times an I gives me an overall negative, right? So this piece times this last piece over here should give me an overall negative because I have an I times an I gives me a negative 1, negative, negative. I have 3 negatives. Take away 1. I take away another one to cancel. I'm left with 1 more negative left, so I have a negative here. And so then I have ijk, I, j minus 1k. In hindsight, I probably could have just left off the k's because they all have the same k. But we'll just continue with it. All right, let's do a quick sign check here. So I have a negative I here. I have a positive I here. I have a positive here because I have negative I squared. Here I have negative I squared. It gives me a negative over there. Okay. Okay, before we make this a little more complicated, let's try simplifying a little bit. I'm dividing by an I out here. I've already canceled these dx's out here in front. Now let's take this I in the denominator and let's distribute it into everything here. So this thing's going to get divided by I. This thing's going to get divided by I. This thing's going to have its I go away because I divided by I is still 1. This will have its I go away. This will have its I go away. I go away. Divide by I, divide by I. Now remember, we're expecting this expectation value of momentum to be real because I can't measure a complex or an imaginary momentum. And yet I've got i's in the formula here and I don't see them canceling out here, right? Because I should expect to see these two cancel out with these two. But oh dear goodness, that's not going to happen, right? Because this is real, 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 real. This is imaginary, 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 imaginary. What are we going to do? Well, the thing is, this is only one term in this entire summation. Remember, we're summing over all the possible values of j. What that means is we need to not just look at this, we need to look at the next term as well. So let's add on to this the next term, the j plus 1th term. So this is j plus 1. So what we're going to do, we're just going to copy this whole thing down. I'm going to add 1 to everywhere that there is a j. So like, for example, in this first part, I've got r j plus 1k, r j plus 2k over I, minus r j plus 1k, r jk over I, right? So this j got moved up by 1. This j minus 1 got moved up by 1. It just became j. Plus, and now before we go any further, I want to show you what happens here. See how here I've got an rj and an rj plus 1? I can flip that around, right? I can call that an rj and an rj plus 1. Look at what I have up here. I have an rj and an rj plus 1. So in the jth term of the summation, I've got an rj plus 1. Down here I've got an rj plus 1. I've got the exact same thing. This one has a minus sign. This one has a plus sign. And even though this is an infinite summation, even though there's an infinite number of terms, this term's going to cancel with this term. That's what we're going to see happen throughout this computation here. We're going to see that one term in this piece is going to cancel one term in this piece. So let's move on here. We're going to have an rj plus 1k, ij plus 2k, all right, minus rj plus 1k, ijk, right, because j minus 1 gets promoted up to j. All right, let's do the next line here. So I'll have a minus ij plus 1k, rj plus 2k, right, I've got to increase all the j's by 1, plus ij plus 1k, rjk, right, yeah, plus ij plus 1k, ij plus 2k, divide by I, minus ij plus 1k, ijk, divide by I. And again, you can see a similar match here. right? Because I've got an ij plus 1 ijk. Here I've got an ijk, ij plus 1k. It's the same thing. They're just occurring in different terms in the summation. Opposite signs. So these two are going to cancel. You notice that that doesn't happen with the real pieces. So like this real piece here doesn't have an I underneath it. rjk, ij plus 1k. Let's look down in the next term. Is there something similar? I've got an rjk, ij plus 1k. Same sign. Those two are not going to cancel, which is a good thing because they don't have an I. So everybody with an I is going to cancel. And you're looking at this and you're saying, well, where does this term cancel? This jk, j minus 1k? Because I don't see any jk's, j minus 1k's here, right? I see, where the only other place I see an r times an r is j plus 1, j plus 2. So where are those going to cancel? They're going to cancel in other terms. So this one's going to cancel with something in the previous term up in j minus 1. Right? You can go to the j minus 1 term, cancel that. This thing will cancel with something in the j plus 2 term. Right? Because you can repeat this over and over again. There's an infinite number of terms in the sum. You can keep going in those directions and cancel those things, which is really cool. The only thing it doesn't happen to is to these things that aren't divided by I. So those pieces will cancel. This piece will cancel. This piece will cancel. Everybody that's got an I in the denominator is going to cancel. So what we're going to do, we're going to get rid of everything that's been slashed out. We're going to clean up the pieces that haven't been slashed out. We're going to put this in our code. We're going to use that to calculate the expectation value of momentum. All right, let's scroll down to that part that we skipped over previously, where we are calculating these expectation values. So here's where we define functions to calculate the expectation values. First, let's look at the expectation value of x. So we need to take an integral of psi x psi to determine x here. Actually, it's going to be psi star, but those both combine into the modulus. So here we've got our integration loop. You always start out with 0 for your integral. And here we've got our psi modulus squared times x times dx. That comes out pretty straightforward. The momentum, like we just saw on the chalkboard, has to be a little bit more nuanced. So here we create our integral psi p psi. And so we've got our real part times our imaginary part to the right, minus our real part times our imaginary part to the left, minus our imaginary part times our real part to the right, plus our imaginary part times our real part to the left. And so this is a result of canceling out all that stuff with the i's. This is only the real parts that survive. And you notice it's only parts that mix real with imaginary. So for x, you only get parts that combine real with real and imaginary with imaginary. For p, you only end up with terms that have real with imaginary. And then here is our h bar, or negative h bar over 2 that we ended up with on the outside, and that's going to turn for us our momentum here. We can do a similar thing for the kinetic energy. So here we go through the same process for the kinetic energy. I'm not going to show you that derivation. That will be left for you to do as an assignment. But we end up with this negative h bar squared over 2m dx, just like you have in the Schrodinger equation. Coming back to the potential energy, that's much more straightforward to graph, to calculate, because there's no derivatives involved. So we just have psi modulus squared times the potential here. Now I don't have any of those graphs on here yet. So to turn on those graphs, you come up to line 38, and we're going to show, we're going to turn this to true to show us the graphs of position expectation value and momentum expectation value. Let's click run again. So I get the same animation window up here for the wave function, right? This is the thing that's really going on at the quantum mechanical level. And then this is the stuff that you observe is the expectation values. So here's our expectation value of x with respect to time, our expectation value of momentum with respect to time. They are just big enough to not fit on the screen together. But what I want you to notice here is that the expectation value of x is following a cosine pattern. And remember, we're working with the harmonic oscillator here, right? This x squared potential, right? You know from classical mechanics that a particle in a harmonic oscillator on a spring with a potential energy of x squared should have a cosine for its position and a sine for its momentum. And that's exactly what you get for the expectation value.
And so even though the particle itself is governed by this wave function, even though we can only talk about the probabilities, the expectation value still obeys the classical equations of motion. That's something we call Ehrenfest's theorem. It's a very important feature of quantum mechanics that's kind of difficult to see in terms of the equations, but here on these animated graphs, it's very easy to recognize this expectation value as a cosine and as a sine. And so it's wonderful to know that even though all this weird stuff is happening with this probability stuff at the quantum mechanical level, the expectation values still obey all those classical laws that we learn in classical mechanics.